it's time to start connecting the concepts we've learned about light and the quantized nature of energy given off from objects to atoms. So what happens if you start exciting an atom, okay, it will give off light. And the way it gives off light, we can refer to kind of three different things. So one, the emission spectrum of that atom. So what is an emission spectrum? It is, let's see if I can find an example. Here's an emission spectrum. So for white light, I should say, like an electric arc is a source of white light, or the sun is a source of white light. If you take this and break it up through a prism, you'll see the entire rainbow. Okay, certain atoms, or I should say atoms, give off their own unique emission spectrum. This is an emission spectrum, again, is just a generic term for either of these things. So these are called emission spectra. Okay, this is called a line spectrum, so it's a type of emission spectrum. A line, I almost wrote line emission, but it is a line spectrum. Line spectrum. Okay. So here we've got hydrogen gas in this container, and we're applying a large voltage across it, right? So we are bombarding these hydrogen atoms with electrons, right? Electrons are sources of energy. So we're bombarding these hydrogen atoms with electrons, and what we're noticing is that it's producing some very particular types of light, okay? And the higher the wavelength of light the higher the frequency of light, the lower the wavelength. So this is lower energy light, this is higher energy light, but you'll notice that there's only particular bands of light. These are particular lines of light. And this is a big hint as to the nature of atoms. So it tells us about the electron states in atoms. Electrons can only occupy particular energy states in an atom, okay? And when they fall back from an energy state, let me see if there's a good picture. Yeah. So here is different electron energy states, and it is related to the distance from a nucleus. N equals 1, let me zoom in here. So N equals 1 is this furthest in circle, N equals 2, right, N equals 3, etc. So when they fall back down, the farther these electrons fall, the higher the energy light they emit. So you'll notice that here this electron is falling from N equals 3 to N equals 2. And it gives off red light. Okay? Falling from N equals 4 to N equals 2 gives off green light. Falling from N equals 5 to N equals 2 gives off blue light. So blue is higher energy than green, which is higher energy than red. But they can only occupy these discrete states. That is the quantum mechanical model of the atom. Okay? Or I should say that is the beginnings of it. That is Niels Bohr's model of the atom, that electrons only occupy discrete states, energy states. And what I mean by that is that we're not saying that the electron I'm not saying the electron is occupied at a particular point out here, but what I'm saying is that it can only be at this energy state, kind of this ring out here. Okay, and I'll come back to that, what I just said, in just a minute. But it can only occupy these states. It cannot occupy the space in between here. Okay, because we don't see a continuous spectrum, right? If that were true, if electrons could occupy any space, we would see this. We don't. We see this. Therefore, electrons only occupy particular spaces. Okay, that's the big takeaway I want you to take from this video, is that electrons only occupy particular areas. They cannot occupy the space in between. And the mathematics for why is actually fairly complicated. But that is how the way we figure that out, though, is from these spectra. Okay? And if we look, I actually had you guys do something similar to this, but I don't know that we ever drew this profound of a conclusion. So this is something we did in chemistry last year. So if you look, let me set the energy at collision down. So let me lower this. Okay, so here's the ground state, and here's some other state higher than it. If I fire an electron and the energy isn't high enough to knock it into a higher state, we'll notice that there's never a photon emitted, right? Okay, if I push the energy up higher to 2, it goes, I'm emitting a particular wavelength of photon. Okay, let me push it up even higher. I'm going to turn it to continuous now, just so I can pause it. So let me try to catch one of these. Okay, so do you see how we knocked it up here to this state up here? I think this is state 3, and when it fell from 3 to 2, see how that's a smaller fall? It emitted a red photon. And now when it falls from 2 to 1 down here, the ground state, that's going to produce an even, so, sorry, let me back up. 3 to 2 is a pretty small fall. So it produces a red photon, which is low energy light. 2 to 1 is a pretty big fall, and that's going to produce a higher energy photon. It's right there. Okay, so this thing right here is an ultraviolet photon. Let me keep going. Okay, that time, even though the energy was sufficient, it only went from 2 and then back down to 1. So it releases the ultraviolet photon. Let me turn this up even more. So what we'll notice, I'll turn this above 6. Let's play. Okay, so it went all the way up here, and it fell all the way back down. So we got another ultraviolet photon. All the way up, all the way back down. 2 to 1. Okay, right there. So this one, I know it's hard to see in there. I don't think I can make it any bigger, unfortunately. But if you notice, we've got a very small fall, and it's a red photon. So these give out, actually, I think it tells you the symbol right there. So it's at 3, okay, so it went from 3, 2, 1. Let's watch another one. 3, 1. 5, 2. So from 5 to 2, that's a fairly large fall. It gave off a blue photon here. And then from 2 to 1, ultraviolet. 5, 2, blue photon. 2, 1. 2, 1. 6, 2. 6, 2 gave off a violet one, not ultraviolet, but visible light spectrum. But that's how this works. Okay, because these only are able to give off certain types of light, we know that the electron can only be at certain energy states. Okay. I think that's all I want to say for this video.